In this video, we're going to start discussing the characteristics of a proton NMR spectrum. As we previously were discussing, when it comes to NMR spectroscopy, we are going to be looking at a specific nuclei to get structural insight on our organic compounds. When it comes to proton NMR, we are going to be laser focusing on the proton nuclei that are present in the molecule. Now, the NMR spectra contains a lot of structural information, which include the number of signals. As we're going to be exploring in this video, the number of signals pertains specifically to the different types of hydrogen that are going to be present in the compound. Later, we are going to be observing what is chemical shift, which tells us what is the signal location in correspondence to the different atoms that are going to be surrounding our proton nuclei. We're going to then proceed to talk about signal intensity, which is the area under the signal. That is going to give us an idea of the relationship in terms of ratio between the protons that are present in the molecule. And lastly, we will be talking about the signal shape. The signal shape or splitting pattern actually pertains to how would the protons within a molecule are going to allow each other to create a specific order of peaks depending on what is neighboring a specific type of hydrogen. Now, as I mentioned, we are focusing in this video specifically with the number of signals. So the number of signals in a proton NMR is going to indicate the number of different kinds of protons that are present in a particular compound. We are first going to be looking at protons that are chemically equivalent. So these chemically equivalent protons, as you can see in the bullet point number 2, corresponds to identical protons. There are two classifications for these type of protons. They can either be homotopic or they can be enantiotopic, and we are going to define them and give examples of them. First, a homotopic proton is going to be specifically found in the molecule in which there is an axis of rotational symmetry that allows one proton to be rotated into another one. So understand that in the basic idea of how we see these, and there are 3 examples of homotopic protons in the bottom of the slide, what we are going to see specifically here is that if we rotate the molecule through a specific axis, we are going to interchange. So those protons are actually going to be in the same position. So if we look at the molecule, the first molecule given, the 2 protons, to do vinyl protons that are in that alkene, we can envision that if we rotate it along this axis, those protons are going to be interchangeable. If we look specifically at the second example, which is that dihalide alkane, if we look through this axis and we have rotation, then those 2 protons are going to be interchangeable. Lastly, in the third example, which is that cyclopropane, we can visualize how the 2 protons that are in the cyclopropane, if we rotate it through this axis, they are going to have symmetry. So what I mean with interchangeable is just that when you do the rotation, they are going to be placed in the same position, okay? And that's what makes them homotopic. So for homotopic protons, we also have another test that it is one that is commonly used. So instead of looking at different axes of rotation, the test in which we are going to do the replacement of the protons is actually a common practice. Now, let's understand that in this technique, what we are going to be doing is looking at 2 protons that are sitting on the same carbon, okay? So if I label this, the carbon that I labeled in red, as you can see, has 2 protons. Utilizing the technique of replacement test, what we're doing is that we are going to exchange the protons one at a time by a specific atom. Here in the slides, you can see that what was drawn is atom D. You can just do any atom in the periodic table, preferably the halogens, just because it is very specific, but you can utilize any atom. So, as you can see, an atom is placed in the position of the proton, and then you're going to also write as a pair the replacement of the second proton, and then you're going to be comparing both molecules. If you notice that the resulting compound is identical to the first, then that means that those protons that you replace are going to be homotopic. Understand that this second replacement test is what is commonly used throughout this presentation in order to determine the classifications that I just mentioned when it comes to the types of protons that we can have in a molecule. Let's proceed. As I mentioned, there are also chemically equivalent protons that are considered enantiotopic protons. Understand that enantiotopic protons are going to be present in a molecule in which the plane has a reflection and it makes the proton a mirror image of each other. Specifically, as you can see in the bottom, we have 2 examples of enantiotopic protons. So, at first looking at this, you may observe in the molecule, okay, I can observe how here these protons are going to have a plane of reflection. But let's actually implement the replacement test so we can look at more closely how enantiotopic protons are actually produced. So, utilizing this replacement test, as I mentioned, is what is going to be utilized time and time again in order to define the different types of signal. If we utilize the first molecule that we had in the previous slide, let's say that we are comparing, and again, it's always a comparison between protons that are sitting on the same carbon. And using the replacement test, what I would do is that I will replace each of the protons by an atom. Here we chose the letter D. You can choose a halogen, for example. And then you're going to compare the 2 molecules that result after the replacement. It's not really a product because you're not doing a reaction. Now, when those 2 molecules are produced, then you're going to determine what is their relationship. As you can see, from the replacement test, what we actually generated, if I focus on the carbon in the middle, is that these 2 molecules are enantiomers of each other because the replacement of that hydrogen, and again, the replacement is just for study purposes. There's not a chemical reaction replacing anything in the molecule. When we look at the 2 molecules, we have created a new chiral center, and then the molecule on the left compared to the molecule on the right are going to be mirror images of each other that are non-superimposable, so they are enantiomers of each other. So that's how we know if we have enantiotopic protons. So to determine if a proton is equivalent, okay, you can look specifically at the rotational symmetry. If you don't have any of that, then you will look at the plane of symmetry, okay? So remember, when it comes to this, you're going to be looking at, do I have an axis of rotation? If the answer is yes, then that means that what you have is a pair of homotopic protons. If the answer is no, then you will be thinking about, does this has a plane of symmetry? If it has a plane of symmetry, then that means that you have enantiotopic protons. Now, if that plane of symmetry does not exist in the molecule, understand that then the protons are not chemically equivalent. Because remember, when it comes to homotopic and enantiotopic protons, specifically, these are going to be chemically equivalent. So when we look at it in terms of a signal at the level of the NMR, they are going to be illustrated as one signal. So let's now look into specific molecules that do not have a rotational axis and they do not have a plane of symmetry. Okay, so this is going to constitute the formation of diastereomers. So going back to our useful technique of replacement test, here we have a molecule in which we are comparing two protons in the molecule. So these two protons, again, if we participate in the replacement test, once we replace them, because there is an existing chiral center in the molecule, and as you can see that existing chiral center, I highlighted it in blue. Once you create by the replacement that new chiral center, understand that since the molecule already has a chiral center present in it, then the two resulting molecules after the replacement test are going to be diastereomers. So it is said that the relationship between the protons is going to be diastereotopic. Understand that when we have diastereotopic protons, they are not chemically equivalent. So what this means is that these protons at the level of the NMR spectrum, they are going to individually give a signal. So let's actually look at a specific example. Remember, if the protons are neither homotopic nor enantiotopic, then they are not chemically equivalent. Let's consider specifically the hydrogens present in the following molecule of 2-butanol. We have two protons that I'm highlighting in purple. And as you can see, specifically in this molecule, we have an existing chiral center, which I'm going to highlight in green. So this carbon atom, it is already a chiral center. Now, these protons cannot be interchanged by rotational symmetry or reflectional symmetry. So what will happen specifically for this example is that let's consider the replacement test. As we have discussed in the replacement test, what we're going to be doing is redrawing our molecule, in which now we are going to be replacing the hydrogen by a different atom. We can use, the fictitious atom D. And then we're going to also draw the molecule that it is paired with, corresponding to the replacement of the other hydrogen. Then we compare the resulting molecules to determine if those two protons that we first had in the molecule are homotopic, enantiotopic, or diastereotopic. So when we compare the molecules that result from this replacement test, we can see that the original molecule had already a specific chiral center. The replacement test introduced a new chiral center that I'm highlighted in yellow. So that means that for this example, these two molecules are going to be diastereomers of each other. So that means that because after the replacement test, those two molecules are diastereomers, then the relationship between these two protons is diastereotopic. So, in summary, when it comes to determine the number of signals, these are the steps that you should follow in order to determine if a particular molecule is going to have chemically equivalent protons or is going to have non-chemically equivalent protons. In other words, you're going to be determining if a particular molecule is going to have homotopic, enantiotopic, or diastereotopic protons. So, rule number one, if we are looking specifically at a signal, and here we have an example of two different molecules, understand that in the molecule that we have on the left, the two protons that are on the CH2 group specifically will be equivalent if there is no chiral center in the molecule. So as you can see here, if I highlight specifically in pink this carbon atom that is holding those two protons, they are going to be chemically equivalent because in the beginning they are not specifically a chiral center. Okay? Now, how do I know that there's no chiral center? Look at the molecule, which I'm going to now write a dotted line. The molecule, if you look at it in half, it looks the same in the top part, in the bottom part, as we move along. Let me just highlight those bonds. As we move along this side of the molecule and this side of the molecule, see that there's no point of difference? So that means that specifically in this molecule, those two protons are going to be chemically equivalent, and specifically, they are going to be homotopic, because originally in the molecule, that center doesn't have a chiral center. Now, let's say that this molecule, now we have the introduction of a chiral center. And as you can see, I'm going to highlight this chiral center right here in a grayish brown color. So if you have a CH2, that then we have already a chiral center within the molecule, understand that they are not going to be chemically equivalent, because that is going to result in having diastereotopic protons. Understand that if you have 3 protons on any methyl group, they will always be equivalent to each other. And lastly, if you have multiple protons that are equivalent, if they can be interchanged through either rotation or a mirror plane, they're going to be chemically equivalent. So for example, when we look at the following ketone, okay, specifically here, in this ketone, we can see how if I highlight in green the carbon atoms that are on either side of that carbonyl group, they're going to have the same chemical environments. Okay, so specifically in this molecule, which is 3-pentanone, those 4 protons are going to be chemically equivalent. And even the CH3s that are at the end of it, so remember there are, I'm going to highlight them in orange, the CH3 that are here, okay, they are also going to be chemically equivalent. But more importantly, similar to the shortcut that we see outlined in number 3, all the hydrogens, specifically in the CH3, are going to be equivalent to each other.